Welcome to my video course on engineering FRMCS. Today, we're zeroing in on one of the absolute most high-stakes, uncompromising areas of railway engineering, and that is emergency handling and communications. You know, when a critical incident happens out on the tracks, the communication network literally cannot hesitate. It has to be intelligent, it has to be autonomous, and it needs to be strictly disciplined. So in this explainer, we're going to explore the precise mechanisms that actually make all of that possible. We'll unpack exactly how the network handles late entries into active danger zones, how dynamic floor control steps in to prevent total chaos on the radio channels, and how rigorous system audits make sure that every single millisecond of an incident is perfectly recorded. Okay, let's dive right into this. We've got 3 core modules on the agenda today. First up, we're looking at managing dynamic late entry. Then we'll hit preemptive floor control. And finally, we'll wrap things up with system audits and logging. Let's get started. Module 1. Managing dynamic late entry. Let's talk about managing these hazard zones. Okay, I want you to picture this. There's a severe hazard on the track. A railway emergency communication, or REC call, is already active between local dispatchers and the nearby trains. Suddenly, a brand new train moving at incredibly high speeds unknowingly crosses into this active danger zone. Which brings us to a massive engineering question. How does the server dynamically push a call connection to a train entering an active danger zone? Think about it. We absolutely cannot rely on a train driver to manually dial into a call while they are hurtling toward danger. The system has to autonomously monitor the network, securely identify this fast-moving variable, and rapidly pull them into the ongoing emergency call. And it has to do all of this without a single moment of human intervention. So here is exactly how the backend pulls off this critical task in literally milliseconds. Relying on continuous location reporting from the mobile clients, the server first detects client eligibility, meaning it knows the exact fraction of a second a train breaches the predefined area of the emergency. But it doesn't just let anyone into a secure channel. It instantly checks the functional alias and permissions to verify, okay, is this a train driver or an operational role that actually needs this alert? Based on that evaluation, the system immediately redetermines the active group members and then autonomously pushes an ad hoc group call invite directly to that train's communication system. Boom! Just like that, they're connected. The sequence of events here is just brilliant back-end logic in action. With a REC call already established, the FRMC's server is continuously monitoring the whole situation. The very moment it determines that a new client meets the criteria to join, simply because they've entered the danger area, it fires off a participant invite. Once the client's onboard system automatically responds, the REC call is instantly modified. That newly arrived train is now fully integrated into the emergency media and the floor control system, keeping the driver safe and immediately informed of the hazard ahead. Moving right along to Module 2, preemptive floor control. Because once everyone is connected, we desperately need to establish order on the channel. Right, so now that our newly arrived train is connected to the emergency audio channel, we're faced with a real behavioral challenge: human panic. If multiple drivers and dispatchers all try to talk over one another at the exact same time, critical instructions are just going to get lost in the static. And this introduces a really vital concept, which is preemptive floor control. In a single-user talker setup, which is the standard for these types of critical alerts, this is the mechanism that grants designated users an overriding, higher priority to instantly interrupt and seize the audio channel from whoever is currently speaking. A strict, technologically enforced communication hierarchy is absolutely non-negotiable here. We have to ensure the most important voice is always the one being heard. Let's contrast exactly how this priority is handed out. On one side, we have the dispatcher or the controller. The system is specifically engineered so that their floor priority number is always higher and their authority is explicitly preemptive. So if a train driver is currently speaking, maybe describing an issue, and the dispatcher realizes they need to issue an immediate network-wide stop command, the dispatcher just presses their button and instantly overrides the channel. Now, non-dispatchers, like our train drivers, they operate on a strictly configuration-based lower priority. They can request the floor, sure, but they can never ever talk over the dispatcher who is actively coordinating the rescue. And that brings us to Module 3, System Audits and Logging. It is time for the post-event analysis. Let's assume the emergency is resolved. The dispatcher took control. The trains were halted safely and a disaster was completely averted. Fantastic. But operationally speaking, the job isn't over. We need to reconstruct the entire event to understand exactly how the system performed and to ensure full accountability. So, operations and maintenance supervision requires some highly specific metadata to be logged. First up, unique source identification. We need to know exactly which radio module generated every single log record. Second, precise timestamping. This lets us perfectly sequence events, like exactly when that late entry invite was sent versus when the floor was actually preempted. Third, we need accurate location data. And finally, perhaps most critically, all of this has to be configured as immutable records. This alteration protection ensures that the incident logs are completely tamper-proof. It gives us a perfect, reliable source of truth for our post-analysis. As we wrap up our analysis today, I want you to consider the future for a second. We've seen just how perfectly synchronized these systems have to be today, but how are these dynamic emergency mechanisms going to evolve as train speeds keep increasing and network densities become even more incredibly complex? Are we going to see artificial intelligence predicting train trajectories to initiate these late entry protocols before a boundary is even crossed? Honestly, the engineering challenges ahead are truly fascinating. Thanks, we can see you next video.